Today we're going to talk about the Pythagorean theorem and applying it in geometry. So first of all, we're going to start off with the theorem, theorem 7.1, which is the Pythagorean theorem. It says that in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So just some terminology to review here. So the hypotenuse, remember, is the side that's opposite the right angle. So in this case, you see is labeled C, which is not touching the right angle. The two legs are going to be the two sides that are actually forming that right angle or meet at the right angle. Typically, you're going to see the Pythagorean theorem written as a squared plus b squared equals c squared. You're going to see that on your formula sheet, and you'll probably also see that some other places around. In today's notes, we're going to see it written as c squared equals a squared plus b squared a lot, and there's a reason for that, which we'll get to later. So either way, really doesn't matter which one you use as long as you're recognizing that c should be the value that's all by itself. So here we're going to use the Pythagorean theorem to find the length of the hypotenuse, which in both cases you can see here is labeled as x. So we're going to start with our Pythagorean theorem, which again we can use a squared plus b squared equals c squared. When we look and label, we know that x is definitely our c since that is the side that's opposite our right angle, which makes it our hypotenuse. As far as which one of these is a and b, it really doesn't matter. So we just need to make sure that we label one a and one b and substitute them into our theorem here. At this point, we're just going to go ahead and simplify. And combine like terms over here, so adding to get 625. And now at this point, we do need to solve for x. So we have to keep in mind, since we're trying to get rid of the squared, we have to think about what the opposite of squaring something would be, and that would be taking the square root. So we're going to take the square root of both sides, which will eliminate that squared, getting us just x. And when we take the square root of 625, we should end up with 25. For the next example, again, we know that x is going to be our c since that's opposite of our right angle. We can label a and b for our other two legs. And once again, just plugging into our formula and solving. That second example, when we're all finished solving it, we should come up with a length for our hypotenuse of 15. The other thing that I want to mention, which I forgot to mention a little bit ago, is that in order for the Pythagorean theorem to work, it must be a right triangle. So if you notice, both of these are clearly right triangles. The Pythagorean theorem will only work in a right triangle. Next example. So here we have a door. A 6-foot board is resting under a doorknob, and the base of the board is 5 feet away from the bottom of the door. Approximately how high above the ground is the doorknob? So we take a look at our diagram. Here's our door. We have this 6-foot long board, which is resting up against the door below the doorknob. We can see that the base of that board is going to be 5 feet away from the base of the door. So we're trying to solve for x here. We're going to come back to our Pythagorean theorem once again because we have a right triangle and we want to find one of the missing lengths. Now when we label this, so we can see here's our right angle. So the side opposite that, which is 6, is going to be our c. That's going to be our hypotenuse. The other two doesn't matter how we label, but we need to make sure one is a and one is b. I'm going to take those values, substitute them into our formula. And if you notice, this one's going to be a little bit different because we're solving for one of the lengths and not the hypotenuse. So algebraically solving it, it's going to be a little bit different. But first step is still going to be to simplify. And then instead of just combining like terms, we're actually going to have to subtract this 25 over to the other side. Then to get rid of the squared, we're going to go ahead and take the square root. Now, if we leave that in radical form, we have the square root of 11. Since the problem says approximately how high that is, we can actually go ahead and take the square root in our calculator and get a decimal approximation. So if we round to the nearest tenth, we should come up with about 3.3 feet. All right, moving on down, a Pythagorean triple. So these are specific sets of numbers where we have three positive integers, a, b, and c, that satisfy the equation of the Pythagorean theorem, which is a squared plus b squared equals c squared. An example of some of these Pythagorean triples. So we have the 3, 4, 5 triangle. And basically what this is saying is that if I have a right triangle, if I plug into my Pythagorean theorem, if I plug in 3, 4, and 5, we're going to see that when we simplify that, they are in fact equal. So again, these are a special set of numbers where they are all integers and they fit the Pythagorean theorem. So we call them Pythagorean triples. Another set of numbers that would fit the Pythagorean theorem would be 5, 12, and 13. I also have 8, 15, and 17. And 7, 24, and 25. These are numbers that you do not have to memorize. You can certainly get these and solve for these using the Pythagorean theorem. But if you know them, you can often answer questions a lot quicker. We could also form other Pythagorean triples using these base triples. So for instance, if I took a 3, 4, 5 triangle, if I multiplied all those measurements by 4, we would come up with the lengths of 12, 16, and 20. If you plug them into the Pythagorean theorem, you will find out that both sides will be equal to 400. So we can create even more triples by multiplying those base triples by other numbers. And again, this is not something that's critical that you have memorized, but it does help you solve problems quicker when you are asked to do like a multi-step problem, or possibly even just to save you some work if you are working through an easier problem. Here's an example. Certainly you can go through and work through yourself. I'll go ahead and solve it up here and then check your answer when you're done. Once you solve that, get it all simplified down, you should have ended up with a length of 51. Now, some of you may have looked at that and you may have recognized that these numbers are actually a root of a Pythagorean triple. If I were to divide both of these by 3, we see that those two lengths would be 8 and 15. Remember that one of the Pythagorean triples that we talked about was 8, 15, 17. So if I were to take that third side and instead multiply by 3, we would end up with 51 as well. So if we think through a little bit more critically with that and use those Pythagorean triples, we can also come up with that same answer. This next problem is going to be an application of the Pythagorean theorem, so we're going to have to do something other than just solve for a missing side. In this, we want to find the area of the triangle. Area formula for a triangle is 1/2 base times height. The key part about the base and the height is that they must be perpendicular to each other. So in this case, 50 is not our height since it is not perpendicular to our base of 28. So you can see this segment here, which is going through our triangle, is actually going to be our height. So we're going to need to go ahead and solve for that. If I pull out one of those smaller triangles, so basically if I cut that larger triangle in half, I'm just going to redraw it here so that we can see it a little bit more clearly. So we know this measurement was 50. The measurement here on the bottom, since this is an isosceles triangle, it's actually going to be, this altitude is going to split our base in half. So this measurement here would be 14, which would be half of our total base of 28. And then we're solving for h here. So we can go ahead and solve that using our Pythagorean theorem, since it's a right triangle and we're trying to find one of the missing lengths. So we'll go ahead and plug in our values into the Pythagorean theorem. Remember that C, which is the hypotenuse, must be by itself. So make sure that you have 50 over here as your C. It doesn't matter which the H is, either A or B, as long as you have that 50 by itself on the right-hand side. In this case, we're going to go ahead and subtract 196 from both sides. And then take the square root to get rid of that squared. And we should come up with a height of 48. All right, so once again, we're not done, but we did find our height, which is the thing that we were missing. So we can now come up here to our area formula. We can plug in our values, which we now know that our height is 48. We know that the base of this total triangle is going to be 28. So we'll have 1/2 times 28 times 48. When we multiply that, simplify that out, we should come up with an area of 672. And then remember that our area units are going to be feet squared. Next, we're going to move on to the converse of the Pythagorean theorem. And this is just saying the reverse. It's saying that if the squares of the legs of the longest side of a triangle is equal to the sum of the squares of the lengths of the other two sides, then the triangle is a right triangle. So that's a lot of words. To kind of break that down, basically what we're saying is if c squared is equal to a squared plus b squared, if that is true, then we know that it must be a right triangle. In the previous part, we were told that it was a right triangle, so we knew that it fit the theorem. Now we're saying that if those numbers fit the theorem, we know that it must be a right triangle. So let's take a look at some examples here. With this, if we're trying to determine whether it is a right triangle, we cannot just make assumptions and say, well, this looks like a right angle, or maybe this line looks to be slanted a little bit left or a little bit right, so it's not. We cannot grab our protractor and measure it and say it is or is not 90. We have to prove algebraically that it is or is not a right triangle. So we're going to fall back on that Pythagorean theorem. We're going to plug in our numbers again. In this case, we don't really have a hypotenuse necessarily because we don't know that it's a right angle, but that C must be our longest side. And you can see here that our longest side is going to be 3 root 13. Go ahead and simplify. Key part of simplifying this over here in your calculator, make sure that you either use parentheses around the 3 root 13, or you want to make this into a decimal first and then square that answer. It would encourage you to just use parentheses and square. Otherwise, you're going to get a different answer. So when we simplify that down, you should get 117. On the left side, if we finish simplifying, you should also end up with 117. So because both sides are equal, we know that it fits the Pythagorean theorem, which tells us that this must be a right triangle. Let's go ahead and take a look at the next one. Again, we know that our longest side must be C, and then the other two sides, it doesn't matter. We can label either one as A or B. We'll plug that into our theorem and see if it's true. When completely simplified, you're going to see that the two sides are different. The left side is equal to 832, right side is equal to 841. So since they are not equal, this is not a right triangle. Now, some of you may be wondering, if it's not a right triangle, first of all, is it a triangle at all? And second of all, if it is, would it be acute or obtuse? So let's go ahead and let's take a look at our next two theorems, which will answer that question. Theorem 7.3 says if the square of the length of the longest side of a triangle is less than the sum of the squares of the lengths of the other two sides, then the triangle ABC is an acute triangle. So this is where it's helpful to have that c squared written first, because when we look at this symbolically, we see c squared is less than a squared plus b squared. Most people are going to remember that that's an acute triangle, because if we think about it as being less than, we think about it being smaller or possibly less than 90 degrees, which would make it an acute triangle. Theorem 7.4 saying very similar thing, except if the square of the length of the longest side is greater than the sum of the other two, then we know that it must be an obtuse triangle. And again, when we look symbolically down here, if c squared is greater than a squared plus b squared, we're going to think about it being bigger or greater than 90, which we would know would be an obtuse triangle. So let's take a look at what these problems might look like. Can segments with lengths 2.8, 3.2, and 4.2 feet form a triangle? So first, to answer that question, we have to make sure that the sum of the two smaller sides is greater than the third side. So if I take 2.8 and 3.2 and add them together, we get 6. And we see that 6 is definitely greater than 4.2. So we know that the answer to that first question, is it a triangle, is a yes. Since it's a triangle, we now have to determine whether it is acute, right, or obtuse. So we're going to take our Pythagorean theorem. And at this point, we don't know if it's equal, less than, greater than. We don't know what that is. So I'm just going to put a question mark here for now. And when we get our values filled in, we'll actually be able to fill that in with a less than, greater than, or equal to. Remember that C has to be our longest side. So in this case, it'd be 4.2. A and B doesn't matter as long as it's your two smaller sides. We'll simplify. And when we get that all simplified, we see that on the left side, which is our hypotenuse, or sorry, our longest side squared, we have 17.64. The sum of the two smaller ones is 18.08. So we see that we have a less than here. Since c squared is less than a squared plus b squared, we know based on theorem 7.3 that this must be an acute triangle. Next one, very similar. Again, we want to confirm that it is a triangle first by adding the two smaller sides together and making sure that that sum is greater than the third side. So if we take 6.1 and 9.4, add them together, we're going to get 11.3. I'm sorry, we're not going to get 11.3. We're going to get 15.5. You see that 15.5 is greater than 11.3. So answer to that is yes, this is going to be a triangle. We're then going to plug that into our Pythagorean theorem to see if it is acute, right, or obtuse. So I'm going to put my longest side squared first, which is 11.3. Again, I'm going to use a question mark because I don't know yet which symbol I want to place in there. Then we have our two smaller sides on the other side being squared. Go ahead and simplify that down. When we get that simplified all the way, we're going to see that 127.69 is greater than 125.57. So because c squared is greater than a squared plus b squared, we know based on Theorem 7.4 that this must be an obtuse triangle. All right, so next up, we're just going to summarize all those theorems together, get them all in one place so that we can see them and have an easy reference. In Theorem 7.2, we said that if c squared equals a squared plus b squared, we know that c is a right angle, and so therefore it is a right triangle. Theorem 7.3, we said that if c squared is less than a squared plus b squared, we know that c is going to be less than 90, so that this is an acute triangle. And Theorem 7.4 said that if c squared is greater than a squared plus b squared, angle c must be greater than 90, so therefore it's going to be an obtuse triangle. All right, taking a look at this last problem, going to be a little bit of a challenge here for you. So you are helping install a light pole in a parking lot. When the pole is positioned properly, it is perpendicular to the pavement. How can you check that the pole is perpendicular using a tape measure? So we're not using a level. We're not just looking at it and seeing, does it look perpendicular? We're going to use a tape measure to confirm that it is, in fact, perpendicular. And this is often really important because if something is not perpendicular, it can cause a lot of other issues. It could cause maybe the pole to fall down or something else to happen. So we do want to make sure that it is, in fact, perpendicular. So let me just kind of draw a little picture here just so we can kind of see what's going on. So here we have our light pole. I know it's a beautiful light pole. On the ground here, let's see, is going to be our parking lot. So we're trying to think about how we can use a tape measure to confirm that it's perpendicular. First thought might be, well, let's measure the height of that pole, and then maybe we can form a right triangle since, we're talking about Pythagorean theorem, and that's all been about right triangles, which is a good thought, but it really isn't practical to measure the height of that entire pole because they're often pretty tall. So what we could do is we could come back to our Pythagorean triples, and we could use one of those Pythagorean triples that would help make those measurements really nice and confirm that it is perpendicular. So I'm going to go ahead and use our 3, 4, 5 Pythagorean triple, which is one of the most used Pythagorean triples that you're going to see. And using this, so what we can say, if we take our pole and if we measure up 3 feet from the bottom, if I then take a tape measure and I measure 4 feet from the base of my pole, I know that if it's perpendicular, that when I measure the distance between those 2 points, that has to be 5. So we can use that Pythagorean triple. We can measure 3 feet up, 4 feet over, measure that diagonal, and if it's 5, we know that it is going to be perpendicular. The tricky part about this is if we know in this direction it's perpendicular, if the pole was slanted maybe forward or backward, that wouldn't change the fact that this would still fit, that it would still be perpendicular because this would still be a right angle. So in addition to just determining that this was or fit the Pythagorean triple, we'd have to pick another point on our pavement here. So maybe I would pick a spot over here and measure out 4 from there, measure out 3 up and check that diagonal and make sure that that was also 5. If we see that both of them fit, then we know for a fact that that's perpendicular and we know that we have installed that light pole properly.